So we are dealing with the seventh problem in this series, and the seventh problem in the series is problem 3.25. The problem is stating a ball of radius capital R carries a positive charge whose volume density depends only on the distance small r from the ball center, as rho equals rho naught 1 minus r by r, where rho naught is a constant. Assuming the permittivities of the ball and the environment to be equal to unity, find the magnitude of the electric field strength as the function of the distance r both inside and outside the ball, and B part the maximum intensity and the corresponding distance at which the intensity is maximum. So over here the ball is not uniformly charged. The charge is varying with distance from the center of the ball. So in order to understand this problem, we first of all construct a spherical ball which the problem is discussing about. So this is the ball we are discussing about, and in this aspect let us consider at a distance r a portion dr. We are selecting a portion dr which will hold a little charge. So over here we have considered a ball of radius capital R, and at this distance small r from the center we are taking a thickness dr, where volume charge density rho equals rho naught 1 minus small r by capital R, and rho naught is a constant. So over here at a distance r, if we select the patch of thickness dr, so we say the volume of a small element, the volume of a small element, so dv equals 4 pi r square dr, and since rho is equal to this, so therefore rho, which can be written as dq by dv, so we obtain dq as rho times dv, which is equal to rho naught 1 minus r by r 4 pi r square dr. So this is the value of dq that we have. So if we integrate this dq from 0 to distance r, so we will get the charge enclosed in the region between 0 to r. So hence to evaluate charge enclosed for a distance r from 0 to r, so we can say from 0 to r, so we say dq equals rho naught 1 minus r by r 4 pi r square dr from 0 to r. So we will get the charge enclosed in this region, and the charge enclosed over here is turning out to be 4 pi rho naught integration r square dr, that is r cube by 3, and r cube by 3, that is r to the power 4 by 4, so by 4r. So this is the variation of charge with distance r. Now if we calculate electric field at a point which is at a distance r from the center, that is over here, say at this point which we refer over here as P, so we are saying electric field inside this sphere, electric field inside the sphere. So we apply Gauss law for this particular region, and we say E dot ds is equal to q enclosed by epsilon naught. So hence we can say that E inside is equal to charge enclosed 4 pi rho naught r cube by 3 minus r to the power 4 by 4r by epsilon naught times 4 pi r square. So over here we get E inside on resolving the terms as rho naught r by 3 epsilon naught 1 minus 3r by 4r. So this is the first part of the problem that we discussed. Now we are calculating electric field outside the sphere. So this is electric field inside the sphere. For outside the sphere, the total charge enclosed, so we can say Q total. For calculating Q total, we have this expression for charge Q. So if we use this expression for charge Q and put small r equals capital R, so we get Q total. So Q in the expression over here we put, so we get 4 pi rho naught. So this term becomes r cube by 3 minus r cube by 4, and over here we get Q total equals pi rho naught r cube by 3. So this is the total charge enclosed by the sphere. Now if we again apply Gauss law, so this is the term that we have. So on applying Gauss law, again, so we say for outside the sphere E dot ds is equal to Q enclosed by epsilon naught. So therefore E outside the sphere is equal to Q enclosed pi rho naught r cube by 3 epsilon naught times 4 pi r square. So this is the value that we have. So now we can say that if we substitute this value for the point on the sphere, that is, if I say for r equals to r, so E on the surface of the sphere, so over here we can write this term as rho naught r cube by 12 epsilon naught r square, rho naught r cube by 12 epsilon naught r square, and E on the surface, so if I put small r equals capital R, so we get rho naught capital R by 12 epsilon naught. This is on the surface of the sphere. So over here we have this as the second part of the problem. So we have calculated magnitude of electric field strength as a function of distance r both inside and outside the ball. Now in the second part of the problem, it is asking us to calculate the maximum intensity and the corresponding distance. So over here we can see that E outside the ball is inversely proportional to r square. So as it is inversely proportional to r square, as distance increases the electric field strength will decrease. So the maximum value of electric field is only possible when E is inside the sphere. So for calculation of maximum value, we are again referring to this part where we have calculated E inside the sphere term. So now we come to the next part of the problem, which is asking us for the maximum value of electric field. The maximum value of electric field. So the maximum value of the electric field, so we say dE inside by dr must be equated to 0, as for outside it is inversely proportional to r square. So E continuously decreases. So if we differentiate the inner term with respect to r, so that is, we have derivative of rho naught r by 3 epsilon naught 1 minus 3r by 4 capital R with respect to dr equated to 0. So over here on solving we obtain small r equals to r by 3. So this is the point at which the electric field is maximum, and hence E maximum. So E maximum can be calculated by putting this value over here. So rho naught 2r by 3 epsilon naught 1 minus 3 by 4r times 2r by 3, and on solving we obtain this value as rho naught r by 9 epsilon naught. So this is the maximum value of field that we have. This is the maximum value of field which we evaluate, and it is at a distance of 2r by 3 inside the sphere. So this was problem number 3.25, seventh problem in this series.